Hello everybody, Mrs. Duncan here with your last official chemistry lesson of the year. We made it. We just have to finish talking about organic reactions, and then I'll have covered most of what I feel is truly important for you to know about chemistry as you move on with your life and potentially furthering your education. With that being said, if you want extra practice at any point on anything we've learned this year, please feel free to reach out to me. You can stop by my classroom next year. I'm not sure where that's going to be yet because my room is being renovated, but when I have that information, I'll let you know. Okay, here we go. We're going to start talking about organic reactions today. Alrighty, so organic chemistry is a really important part of our everyday lives. The reactions that are called organic reactions use organic molecules, so carbon-based molecules. These reactions have applications and uses in pretty much any aspect of your daily life that you can think of. So that includes medicines, the environment, energy, natural products, and synthetic products even. So there are actually a lot of career pathways that use organic chemistry as their backbone. Okay, so there's a bunch of different organic reactions out there. We're going to talk about the most common types of them today. And the first type of organic reaction we've learned about already. We learned about it earlier in the year. This is called a combustion reaction. And if you'll remember, the combustion reaction is what I always say is the fire reaction. So this is the first organic reaction that humans learned how to do. The evidence of the first man-made controlled fires date back about 1 million years ago. So about 1 million years ago, humans figured out how to do this organic reaction to produce fire to keep themselves warm. So combustion reactions have the same general format. There's usually some hydrocarbon, some combination of carbon and hydrogens. That's why there's like an X and a Y there. That hydrocarbon reacts with oxygen in the atmosphere. Remember, we always say fire needs oxygen to burn. The products of every combustion reaction are always the same. You make carbon dioxide and water, and that actually comes off as part of the smoke or vapor you see as something burns. A last product is obviously heat. These are very exothermic reactions, thus they keep you warm in your cave if you're one of the first cavemen who did a combustion reaction. Okay, so I kind of tried to set these historically. The next organic reaction that humans mastered was, you might have guessed it, fermentation. So the first evidence of an alcoholic beverage that was made by the fermentation process was made from fruit, honey, and rice, and it was found in Neolithic China. And its approximate age dates back to somewhere between 7,000 and 6,600 BCE. So basically, humans figured out how to make fire, and then a great amount of time passed, and then they figured out how to make alcoholic beverages. And that was for more than just pleasure purposes. Back then, that was a good way to make sure whatever you were drinking didn't contain harmful bacteria that could potentially make you sick. So how does fermentation work? Well, it's actually pretty simple. You take some sort of organic molecule. Typically, these are sugars like glucose. Usually, you react it using some sort of enzyme. A good one is yeast. Oh, my pen stopped working. A good one is yeast. There it goes. And the products that you would make would be alcohol and carbon dioxide. So the primary form of alcohol that's produced in a fermentation reaction is referred to as ethanol. This is the one and only type of alcohol that humans can consume in reasonable quantities when they are legal age for recreational purposes. In addition, you also make some carbon dioxide gas. So fermentation reactions, the second organic reaction that humans mastered, basically it involves taking a sugar like glucose, reacting it with some enzymes like those found in yeast to make alcohol and carbon dioxide. Next up on the organic reactions is a reaction that's called saponification. And if you look at the first 4 letters of saponification, S-A-P-O, and you rearrange them, they spell out soap. So historically, humans figured out combustion, the organic reaction to make fire first. They then figured out fermentation, the organic reaction to ferment things like alcohols, beverages. And then they found in about 2200 BC, there was a Babylonian clay tablet found that contained a formula or a recipe for making soap. And the recipe was simply water, alkali, which is a strong base, and a form of oil. So saponification is the reaction that makes soap, and we use similar reactions today to make the soaps that you use. Basically, it starts with some sort of fat. Fats are interesting because what you're looking at here, this represents a long chain of carbon atoms with a lot of hydrogens bonded to them. Basically, what you do is you take a strong base like sodium hydroxide and you react it with these fats, these long chain hydrocarbon molecules. That sodium hydroxide, the way it reacts, it basically separates this portion of the molecule off, cuts it off, see right here. And what you're left with is something that looks like this. Soap molecules are very interesting because they're called amphiphiles, which means that one end of a soap molecule is polar, and that would be like this end right here. And the tail end is nonpolar. Why is that important? If you remember back to shortly before classes were suspended, we learned the phrase like dissolves like. This is why soap is so good at cleaning your hands. The polar end of soap molecules mixes with water, because water is polar, and the nonpolar end of the soap molecule mixes or dissolves fats, oils, etc. So you can remove both polar and nonpolar molecules from your hands. Again, the general reaction format here is a strong base plus some sort of fat makes soap. Okay, the next types of reactions that I'm going to talk about are referred to as organic synthesis reactions. These have a lot of uses in our modern society, in particular in the creation or synthesis of things like drugs, plastics, food additives, fabrics, etc. Right, I have here down here example of some organic molecules. This right here is a molecule that is found in a common blood pressure medicine, which is called lisinopril. This is a model of this molecule right here. And basically what you're looking at are all these black atoms right here. They represent carbon atoms. So there are reactions that we do to synthesize molecules such as this, which is a common blood pressure medication. In terms of food additives, you may have heard of this. This is called guar gum. If you look at the back of a lot of the foods, packaged foods that you eat, you'll see that added in. It's found in things like ice cream, salad dressing. It's an emulsifier. Basically, it's something that makes a product thicker. Like you can think about thickening up ice cream to a texture that you would want to eat it. These are rings of carbon atoms that are all joined together. The last molecule I have here actually represents a molecule that makes up nylon, which is a synthetic fabric that we can create through these organic synthesis reactions. You find nylon in all sorts of everyday items, but again, it is an organic molecule because these zigzag portions actually represent carbon chains. Okay, so let's talk about these synthesis reactions. So if you're interested in things like drug design or designing any type of molecule as you further your education, you'll be using these reactions in series with each other. So you don't just use one of these to build a molecule, you use many combinations of them. So a substitution reaction is pretty straightforward. It's when you have one atom or functional group on a molecule and you replace it with another atom or functional group. This commonly occurs with alkanes and halogens. We do that a lot. We take an alkane, like methane, and we react it with a halogen, like chlorine. And basically what happens is we pop off one of these hydrogens and replace it with one of the halogens. So that's, you can see right here, that's what happened. That hydrogen was removed and the chlorine attached. Now, when that hydrogen comes off, it gets together with the other halogen. Chlorine is diatomic. It always comes together in nature in groups of two atoms. So that hydrogen that's removed combines with this extra chlorine that is being reacted and actually makes an acid. In this case, it would be hydrochloric acid. So substitution reactions, a lot of times the format that you see for them is something like this. an alkane plus a halogen, so that's your halogen, that's your alkane. You make a halide because you substitute one of the halogens for one of the hydrogens on the alkane, and then you make some form of acid. Addition reactions are similar to substitution with a couple key differences. Addition reactions generally occur with alkenes or alkynes, usually alkenes though. But you're going to do something similar. You're going to add one or more atoms to a molecule that contains a double or a triple bond. That's why I said this is commonly done with alkenes and alkynes. So similar to what we just saw in the substitution reaction, you have an alkene. This is ethene right here. You would react it with halogen, chlorine again. What happens is we say in this case, the double bond opens. That means it converts to a single bond. Because carbon can always make 4 bonds, when you convert this double bond to a single bond, it allows you to actually go in and add both of the halogen atoms to your carbon chain. So a key difference between addition and substitution is, in addition, you only make one product. You just make a halide, one halide, whereas, bouncing back, whereas in substitution, you make 2 products, a halide and then some form of acid. And again, the reason we only make one product here is because the opening of that double bond allows us to add both of these halogens to our hydrocarbon. All right, the last reaction I'm going to talk with you about, and then we are done, is called polymerization. If you look at the prefix poly and you think to yourself, poly means many, right? So polymers are formed by polymerization reactions, and it consists of a reaction where you make a larger molecule from smaller molecules. And these smaller molecules have a name. They are referred to as monomers. So monomers are like this. They're these smaller identical molecules that you basically react in such a way that they all combine together and make what's known as a polymer. So a molecule made up of many monomers. In nature, polymerization happens quite frequently. It leads the production of proteins and starches. People use polymerization reactions to produce things like synthetic rubber, synthetic plastics, and fibers like nylon that we talked about earlier. This reaction down here is actually a polymerization reaction that happens in our body. This is a synthesis of an amino acid. These 2 molecules are monomers. I know it's hard to see, but because they're rotated, let me just back this out for a second. If you rotate this 180 degrees, this molecule is actually the exact same thing as this molecule. They're just oriented differently. Because you're combining 2 identical monomer molecules together to make a larger molecule, which is referred to as a polymer, this is an example of a polymerization reaction. And again, this is a reaction that synthesizes an amino acid in our bodies. Technically, there's many forms of polymerization. This is called condensation polymerization because water is produced as a product as a result of this reaction. All right. That is it, my friends. Definitely kind of a sad moment for me. I really look forward to this moment every year when we finish and we take a minute and we celebrate. And I really am going to miss you the last couple of days of school where we would just kind of spend some time hanging out, signing yearbooks, things like that. So feel free to reach out to me at any point, whether it be the rest of the school year, whether it be this summer, whether it be next year. I'd love to see you all again at some point and just say hello. Okay, that about does it. The last really official assignment I'm going to have for you, you're going to have one that goes with this video, and then I'm going to post a feedback survey, which, I mean, am I going to put a grade in the portal for it? No, but it would really help me if you could take a moment and answer the questions in the feedback survey as honestly as you possibly can. You will not offend me. Don't worry. I have thick skin, so that I can improve and be an even better teacher next year. All right. I hope I see you all soon. Bye.